diffraction grating and I and E. Right? All right, so let's start, right? All these things you know already, so I just going through it, right? Right. What are the four things that waves undergo? Reflection, refraction, diffraction, and interference, right? So reflection. In the laws of reflection, the incident ray, the reflected ray, and the normal all lie on the same plane, and the angle of incidence equal to the angle of reflection. Refraction, on the other hand, the incident and the refracted rays are on opposite sides of the normal at the point of incidence, and all three lie on the same plane. Right? All these things we kind of know. But look here, refraction here depending on light as it goes through mediums of what? Different densities, right? Right? As it goes through a more dense medium, what is happening? Right. Why? Because it slow down, right? So it slow down and bend towards the normal, right? And the relationship that summarizes refraction is Snell's law. Okay. Diffraction on the other hand is the spreading of a wave which is limited by an obstacle or gap. Diffraction is the result of superimposed secondary wavelets from coherent sources on a continuous section of a wavefront that has been limited by some obstacle. Basically, all that's saying is that it's spreading of a wave, right? I will show you another diagram just now that the wave that produces really a sum of some subwaves called wavelets, right? Right? The degree of diffraction depends on the relative size of the wavelength and the obstacle, right? The smaller the wavelength, what is happening? And then here, the smaller the wavelength, I'm sorry, the smaller the obstacle, what? So the smaller the obstacle compared to the wavelength, the greater is the diffraction, right? So just remember this, please. Which one will undergo a greater set of diffraction? Diagram A or diagram B? B, right. When it passes through here, the diffraction will be like that. When it passes through here, the diffraction looks like this. All right? Some small things to remember. Right? What about interference now? Interference is when two waves meet at a point, the resultant is a vector sum of the individual displacement, right? So you should remember, if you have crest and trough meeting, you have a superimposed wave will be a much larger wave, right? If you have crest and trough meeting a trough and crest, they'll cancel off and give you nothing. Okay? So you have constructive interference and destructive interference here. Interference is the result of superposition of waves from a finite number of coherent sources shown. Right? Interference at a particular point is said to be constructive when waves reinforce each other and destructive when they are self-canceling, right? We are really going to focus on interference today. All right? So, what are the things that affect the interference pattern? All right? So, try to remember this. Whose experiment is this? Young's double slit, right? When the light rays go through here, it undergoes diffraction, right? And what has happened at different points? Right, so when they intersect, you have constructive and destructive interference, right? What happens at constructive interference? Right. So basically, you end up with something like this: a bright fringe with two dark around it, bright fringe again, dark, bright, dark, right, dark, and so on. What you have here, Nikash, is a fringe pattern. Right? What you have there is a fringe pattern. And the separation between them is Y. Everybody okay with that? Let's call the Y fringe separation. Right? What we are going to investigate is what are the factors, Saraya, what are the factors that will affect Y? Talked about it in CSEC. Talked about this. Huh? 3 things that affect Y. Wavelength, very good. Right? The width of the slits, how separated the slits are. Right, source to screen distance. So I remember something or learning from recently, right? So those are the 3 factors that are going to affect Y. That's okay? I see you shivering, pay attention. So not going on. Right? Right? So the 3 factors that are going to affect Y, right? Like how far apart they are, how close they are lambda, A and D. Right, Shivish? So focus on those 3 quantities, lambda, A and D. D is here, how far the slits is from the screen. A is how far these slits are. Right here and here, 2 slits. See that? And the wavelength is the wavelength coming. Pardon me? What else? Lambda the wavelength of the light coming in. Pardon me? Here, that's it. Right? So from the fringes, I'll draw them in board just now because we have a little proof to do in a little while, right? Yeah, I'll do this proof. Right? So from the slits to the screen is capital D. Right? Anybody remember the exact relationship? Y is equal to what? Anybody remember the exact thing? F lambda. D lambda on E. Right? So D lambda on E. What is here? For those who are not seeing it, right? Watch here. The separation between the slits is A. Right? You have a screen, and the separation between the screen and the slits is D. Right? And you have fringes. The separation between the fringes is Y. Alright? What we are going to learn now is that Y is directly related to D. Y is directly related to lambda. That's the wavelength here. And Y is inversely related to 1 on E. Right? So if I bring the slits close together, right, Y becomes larger. If I bring D closer to, if I bring the screen closer to the slits, the fringes get smaller. If I use a large wavelength, the fringes get larger. Okay? So this is the formula that we are forced to prove. We have to prove that. Right? Pardon me? Triangle text here. Okay? Right, so let's take a little small read here. Conditions for observable condition. Pardon me? One on who? A. One on A. We'll do this now. In here. Why we share it? So the waves must have an approximately equal wavelength. Oh, these are the conditions for observable interference. Right? The waves must be an approximately equal amplitudes. What would happen if they are not, right? If the wavelengths are not, the amplitude are not the same, then you will have incomplete cancellation at points at points where there is destructive interference and the result is a reduced contrast. So you're not going and see bright and dark, bright and dark. Right? So what will happen here if the waves, right? If the amplitude of the waves at meeting are not the same, then you will not have a nice fringe pattern. You'll have plenty overlap. All right? Next, source must be coherent. Right? What does coherent mean? Coherent simply means that it must be in phase, same phase difference, and they must have the same frequency and wavelength. All right? If this doesn't happen, a time-dependent phase difference between the sources would result in a varying phase difference between the superimposed waves. Well, that means that the waves are not in phase all the time, and again, it will mess up the fringe pattern. All right? So you wouldn't be able to detect the interference properly. Okay, you wouldn't be able to tell where it's constructive and where it's destructive, right? Next thing. The sources must be relatively close to each other so that the waves from them could overlap. So you don't want this, right? You don't want one slit here and one slit here. And then when the waves come out, they're not overlapping. Obviously, you will not get what? You won't get interference, right? And the distance from the source to where the fringes are must be large compared to the separation of the sources. Okay, so what it's saying there is that D must be much larger than E. That symbol means much larger than. Okay, D must be much larger than. Huh? Yeah, greater than. Yeah, much larger than. It's greater than. So it's not just greater than, it's greater than that. If you want to make it greater than, you can do that. For the next one. Right, transverse waves must either be unpolarized or polarized in the same plane. Interference cannot occur if the vectors do not lie on the same plane. So you can't have a wave on this plane and a wave on a perpendicular plane. They will not intersect. All right, they have to be polarized in the same direction. All right. So as I said, we want to focus on interference, right? So let's go ignore that there for now, right? We'll come back in the AM and summary. Right. So what's this here? What I've been talking about all the time is this. Right? When the light comes in there and they pass through the double slit, right? You have that fringe pattern. What is Y in that diagram? What is Y in that diagram? Here to here is Y. Right? Y is fringe separation, right? Where is E? Where is E? Here to here is E. Where is D? Where is lambda? H1, right? Pardon me, sir. All right. So now we have to prove that formula there, right? All right, I'll come back because I want to use the same way that right. So here, clearly online, right? Because it's slow down, right? So you slow down and bend towards forward. All right, so let's take a look at the same thing we were talking about, right? Let's go back to the screen. Oh God, finally I can take this off. All right, so nice. So let's take a look at one second. Let's get a mark. Right, so here's what we're looking at now, right? What we're looking at is we want to be able to get this relationship. All right, again, I'm gonna just make sure you know what every letter is, right? Right, and how do we prove this? Right, I'm gonna draw a nice little setup here for you. You put it in your notes, I just have to get back the right label. I don't want to, I like to use the exact label from the notes. Right, I'll get that just now. Right, so here is something that we need to remember. We need to remember something. When we have our slips, one line, you'll see the slips there, right? Right? When we have our slips, right? We have this light coming in. It's monochromatic light. Mono means one wavelength, right? So we have monochromatic light coming in, and it will undergo the interference here, right? I want to say, remember something, right? Remember from here to here is A, right? I'll draw it a little bigger there because I'll do that whole thing, right? Remember from here to here is D, right? And you have the wavelength, you have D, you have A, right? Good. And you will always, if you look at the fringe pattern, you'll always recognize that the middle or the middle fringe here or the brightest, right? That is central bright fringe. Okay. So if I have a ray, right? Let's say I have a ray, and the ray coming out from here, the ray is going to travel a distance and reach here. Some distance, right? Let's call the distance AB. That's okay? And next ray will leave here at the same time, provided it interferes, and it will travel distance CB. Right? Remember, I told you that this is a bright fringe, right? Remember, I told you this is a bright fringe. Well, what you could say, Nakila, what you could say about the paths that are the travel? CB and CA. What you could say about CB and AB? Did they travel the same distance? Yeah. So we could probably say that they equal. Okay with that? We could say that they equal, or we could say that the path difference is 0. So the difference in their paths is 0. That's okay? Okay with that? So after the central bright, there's a dark and there's a next bright. Online, you're okay, right, Shania? Right? There's a next bright fringe here, right? Let's call this B. This is B1. Let's call that B2. Watch this here. We have a ray leaving A again, going to B2. And we have a ray leaving C, going to P2. Are the paths the same? No, paths not the same. Who traveling furthest? AB2 traveling furthest, and so if I find it, so if I subtract this here, right? Here what will happen? What you will end up with when you subtract that is lambda. Right? If you subtract that, you will get lambda. And here what all this says. What this says is that whenever you have a bright fringe, the path difference, whenever you have a bright fringe, right? Whenever you have a bright fringe, the path difference will always be a whole number of wavelengths. Right? So whenever you reach a bright fringe, the path difference to reach there is always going to be some whole number of wavelengths, right? If you end up at the third bright fringe, and you subtract the path difference, you will get 2 lambda. That's okay? So every time you reach a bright fringe, if you were to subtract the paths, you will always get some whole number of wavelengths. So this is the central bright, there's the first bright, second bright after that. All right? Okay with that? Yeah. Right? Where would you expect to find dark? In between, right? So in between here, you expect to find dark. So if a ray leaves here and it reaches here and it travels here, in between there, you expect to find dark, right? So this is a bright fringes, right? This is a bright. For dark now, where do you all expect to, what do you all think the path difference will be for dark? Right, in the middle there. Right, in the middle. So that'll be a half number of wavelengths. So lambda and 2, here will be 3 lambda and 2, then 5 lambda and 2, so on and so on, right? So whenever you subtract two parts and you get a half number of wavelengths, you are at a dark. Okay? So this is the first bit of knowledge that we need to understand. All right? Okay? When the path difference is a whole number of wavelengths, you're at a bright fringe. When it's a half number of wavelengths, you're at a dark fringe. Are you okay with that? So we're going to use this knowledge now to help us prove. By the way, ignore the red lines if you all could do that, right? Anybody seeing the path difference? Ignore this one. Can you see the difference in the path? Where? This longer than this end? But you can see the path difference. Like what I could do to show how much longer? Yeah, measure it, or you can just draw a line down here. These two parts are supposed to be the same, and this will be the path difference.
It's on right hand, right hand track.
No, we'll use that later on, but no, I just wanted to see that if I were to draw a line down here, that means perpendicular to AB2, I'll be able to get a path difference. So when you subtract AB2 and CB2, this is the path difference. How much is this again? Lambda. You'll see enough? Because that was the first bright fringe. So this length here is supposed to be lambda. Supposed to be lambda. All right? So we're going to use all that now to prove something. Yeah, copy this one down because it's not ready. When I'm going to show it, we're going to have it. Taking this off, right?
Yeah.
I need the whole board for the proof.
Just one minute.
Right here. I need the whole board for the proof. Online, you're with me, sir? Finish? Huh? Yeah? The word is part difference, right? All right, so watch here. Right? This is the first part of the proof. So watch here. Right? I'll print the other label in just now, but I want you to understand what I'm doing, right? So watch here. Right? What I'm doing here is to try to get it through. Okay? Light coming in here, Shabara. Right, so watch here. Light coming in here and it's traveling along the path, the intersection, and again, different pattern, right? Here is the central bright in the middle of everything, central bright, and it's the first bright fringe. We are only focusing on what happening at the first bright fringe. All right? When a ray leaves here, right, it will travel AP. When a ray leaves here, it will travel PP. Right? What is A? Sorry, which is larger? Right. What is BP minus AP? Lambda. Because it's the first bright fringe. Well, whenever you have a bright fringe, right, the path difference is lambda. Everybody okay with that? How do I find BP minus AP? I can draw a line down here. Angle theta. And the angle here is 90. All right? So watch this here. So yeah, that's the important thing, to make sure that this line is perpendicular to BP. Now, this here is the path difference. You're seeing that? I was trying to get the exact letter. What letter did I use there, boy? I have A, B, P, E, O. I use M, P, M. Triangle P. So that means the middle here is M. right? Here would have been M and here would have been N. So what you see here, in order to do the proof, we are going to focus on two triangles, right? We are going to focus on this triangle that gives us the path difference, and the next triangle here, here's a right angle, and here's theta again. These two angles are the same, right? These two angles here will be the same. Yeah. But what I want you to do for me is to draw this diagram, and let's do this proof together. Yeah, straight line, everything straight. Yes, they're all straight lines. Right, but you'll follow how I got the two triangles. I draw a line down here, and this was the path difference. So I'm focusing on this triangle, and I drew a line from P to M, and I focusing on that triangle. They both have the same angle, theta. Right? The entire proof is based on this diagram. Right? And that's the exact note I have there. So use the same labeling, right? A, M, B, and P. All right, copy it down, and let's put this together. All right, so we're going to use this diagram here to prove that relationship. Pardon me? M is the middle, like A and B. Capital E and B. Pardon me, ma'am? This line going to BP, yes, ma'am. Oh, I'm going to P, ma'am, yes. Let me have it double più. Okay. Double not più. No? Right? One thing in doing this proof that I want you to remember I told you that D. Remember I told you that D is much, much bigger than A. Right? So the separation here is much, much bigger than the separation here. All right? So remember that because we need this in part of our proof, right? This theta angle here real small. Because of that, theta is very small. That's okay? So because this so close together and this so far apart, these angles here are really, really small. Huh? Those two angles are equal. But they're really small. No, M is just a random, not random. MPO is just a triangle I'm using to help equate things. MPO, yeah. MPO, and I'm using A and B. Those two triangles are focusing. Huh? Half eight. Huh? We have about one or two more here. I was supposed to finish this second week in March, but I tried to finish a little before because I didn't know. I didn't know Makilam was so far. Well, I will. Yeah, my plan was to finish everything the second week in March. But I didn't realize some other exams. So I would have doubled up and see if I could put it. Can I get markers up? Yeah, what that's going. Absent, all right, ready? Let's go. Right, time for the proof. About 5 minutes. Okay, should we shall a little break there? Yeah, a little break. Right. So what's this here? Once you reach here, the proof's simple, right? Once you have this here, the proof's simple. You have to focus on two triangles. You have to focus on triangle PMO and triangle ANB. Anyway, you wanted to label it, right? Actually, it's supposed to go right. PMO. Let's take a look at PMO. O to P, that distance is what? Well, that's Y, right? O to P is the fringe separation. Remember that? So O to P is Y. Yeah. Right? No. Here is a bright fringe and here is the first bright fringe. So the separation between them is Y. All right? So what is tan theta for, what is tan theta here? For PMO. It will be, right? Tan theta will be opposite over adjacent. So it will be PO over MO. What is PO? PO is what? MO is what? MO is? Did you hear that? Now, let's focus on the next triangle, A and B. What is sine theta? Right? Opposite over hypotenuse. So therefore, opposite is what? No, MN. Opposite is M. Sorry. LBN. Opposite is BN. All right? And here is your hypotenuse. So it will be BN over. Right, but what is BN? And BN is the difference here. So BN is lambda. Yeah? And what is AB? AB is small a. Right? What did I say about theta? So since theta is very small, you would have done this in limits, some people. Since theta is very small, then tan theta is approximately equal to sine theta. So whenever theta is small, these two are the same thing. Right? Non-matched people just accept it, right? These two are equal. So you end up with y over d is equal to lambda over a. That's okay? And then you carry across the d, and you'll get d lambda on a. All right? So in order to do the proof, you need to do three things. Diagram this information and remember this. All right? So that is the proof. Copy it down. The one I did in the notes, instead of doing the first right fringe, I did the nth right fringe. I subtract them and I get the same answer. Okay, but the same label and everything. So the one in the notes Nalia. The one in the nose is not the first bright fringe. It's the nth bright fringe. So I did it twice for the nth and n minus 1 and subtract them to get this back. Same principle. And the two consecutive and a minus them to get 1. Right? So the same diagram, same principle. Copy it up. So you have to be able to do the proof, right? If they ask in an exam to show y is d lambda, you gotta be able to do that. Okay? Proofs are nice. It makes sure that I kind of understand the concept of everything that's going on. Right? Like something really important that one of the years that we'll do is that this year, you have to remember that path difference is a whole number of wavelengths. All these little things, right, was really important in developing the proof. You'll see them in questions. All right, so this is what we need to know with interference. Then we have refraction and diffraction. Yeah, that's a change. So I want to any questions online? No, I give you all do it already. Same principle. Same principle. So do we average? Hi Sonia, one of my favorites. Hi, come back again, but this one. All right, so watch it here. Anybody writing online still? You go to the question, right? All right, so you might see, I'm not sure if all you have seen it's the top part, but basically they investigated the interference of sound and they have two speakers and a microphone. A microphone is moved along XY. It detects a maximum in sound intensity at O and at X, right? So this is exactly what we did, but instead of light, they're using sound, all right? Slits, yeah. The two speaker boxes are the slits, and the O and the X is the what? O and the X is the what? Huh? Fringe separation, bright fringes, right? So instead of bright fringes here and here, we just have loud or maximum. What happened in the middle? No sound, minimum, right? Minimum. It'll be like minimum. It will never be zero, it will be minimum. Huh? Go on. We reach there. We the first part. I don't know what year it is. I won't tell you what year it is. A little one, the fans, right. So take a little read, look at the labeling, don't draw it back there, we don't have time for that. Right? Take a look at it. Find the distance, PX, QX. Right? Find all those things there. Take a look at it. What type of triangles you're working with there earlier? Right angle triangles, right? So you have to remember your little Pythagoras theorem and thing, right? So they want you to find PX, use the appropriate triangle, and they want you to find QX. Use the appropriate triangle. This part one have nothing to do with why it's D lambda and A as yet. No use it. That's part two. Watch here. Read part. That's not. Watch part two. We're trying to use a mathematical way and compare it in formula. Take a little read so you know what's going on, right? So don't use y d lambda e until part two. Right, let's start. QX, PX, sorry. What triangle are you going to use? Area. What triangle are you going to use to find PX? PYX, right, correct. So you're using this chart. So you're using this triangle here. Right? Here is 6 meters. How much is here?
3.75.
How come?
I assume that between wire surveys and not.
Very good. So you kind of split up 1.5 here, which is 0.75. So here to here is 0.75. So the whole length will be right here, 2.5 plus 0.75. Okay? I'm sure that making any sense. I'm going to draw it back here again.
That's basically a half base and half, right?
Yeah. Sorry?
1.5.
No, 1.5. Look at the next side.
Okay.
So here to here is 0.75, and here to here is 2.5. So when you add up the whole length, you get 3.25. Right? And then you're going to use what? You're going to use Pythagoras theorem, right? How you have to what you get?
So 6.8.
And we just get up. And then the Leo, then the Ubu thing, you want to lean on there. Just drop back watching outside.
Yes, that's right.
Right? How much all got to PX? 6.82. Now find QX. 6.5. Right? Nikolai, since you don't understand, tell me what's these lengths, right? First thing I do is figure out the triangle. Right, so you go in here, coming down here, and coming here. Here is 6. How much is here?
1.7.
Right, 2.5 minus 0.75. Sorry? Because remember, here plus here is 1.5. That's okay? See enough? The two speakers, right? The two speakers, same speaker 1 and speaker 2. Right. The distance between them is 1.5. And the central right to be in the middle of 2 of them, right? Huh? So it's half of it, yeah. Right, so we have px and we have qx, right? When you subtract px and qx, what's you getting here, right? No, so that time of what it is. That will be lambda. Very good. So px minus qx is lambda. What you'll do for lambda? Any answers online? Huh? Pythagoras theorem. Any answers to lambda online? Follow it. Lambda is how much? How much? 0.57. Huh? So the part difference would be lambda, right? Why again? Why would the part difference be lambda, Shavish? When you subtract px and qx, why would the answer be lambda? Huh? Why? Or do we have that? Yes, Shavish. Why is it lambda? The fact that the first root there, right? Roots on this. Azaria, why is it lambda? Why is px minus qx? Where reach? We serious in not reach yet? Amanda, why is it? Huh? First loud, or first max intensity. Yes. It won't be bright, it'll be loud, right? It'll be loud in this case. So please remember the part difference, right? The part difference at the first bright will be lambda. Right. So that was the long way to do it. Now use the formula. Part 2, use the formula. Discuss why it's different. That's not Azaria Norwich here. Azaria, we will cover that part 2 now. Use the formula for part 2. Now, what is Yeah, how much you get for lambda? So we know what y is, right? Y is 2.5. We don't know what is lambda. T was what again? 6?
Yeah.
And A is how much?
1.5.
1.5. So lambda is 0.58 meters. Discuss the fact why the values are different, right? So the first lambda was how much again?
0.57.
0.57. And the second was 0.58, right? Why are they different?
The exact values.
And should be a little, it wasn't that close, if I'm not mistaken.
This
2.5 by 1.5 divided by 6.
like 6.5.
Right. Yeah, I remember it being a little bit further. 0 point. Right. Oh, that is why I thought that's so probably. The message. Right. So Azaria, why are they so different? Why is B part 1 and B part 2 so different? Why we didn't get the exact value? Why are they so different? Huh? No, huh? 1995. Yeah. What is this? Anybody? Anybody? Why are the values so different? One row? Not wrong. It's a little off. But why? Why are they so different? Why is it a little off?
After this, the exact values.
Huh? When we were doing the proof, right?
Oh, yeah.
One's an approximation. Look at the proof. What did we say? And we approximate tan theta equals to sin theta. So the formula is an approximation. Okay? So which one will be the more accurate value? First value. Right? So make a note of that, please. The values are different because the formula y is lambda d and a is an approximation. Okay? Y is lambda d and a is an approximation. They might not have all the information to do the first one. This question is given to you for you to do the analogy. But in a past paper, you might not have enough to find value. If you could, yes. If you could, you could go right ahead and use the first one. That's okay? Oh yeah, 2 part 4 and 5. 2 part 4 and 5. Speed of sound. Get it to give in, but it cropped out somewhere.
Yeah, which one? 0.5791 and equals
Oh, which one? 0.57. The first value is the more accurate one because did we do any approximations there? No. Part 1. So. When you work out px and qx, did they do minus it? Yeah. Right? What's the formula we're using to find frequency? Frequency is what answer I have? In terms of lambda and speed, you know? Beyond lambda. Huh? Well, just give you the bottom, but cut it off. Speed of sound is 330. Lambda we're using 0.57. You use the more accurate value. How much is that? How much? 579 hertz, right? Stick to two significant figures, right? 579 hertz. Stick to two significant figures. Last part. Last part is theory. So that will go to Aryan. Aryan. I'll show you playing Tyrese in the back there. Aryan, read the last part. Tell me what your answer is. So now the phase of the speaker changed by 180. What does that mean? Huh? What does that mean? If it changes the phase by 180, what will happen at 1x? Well, there's no fringes here, is maximum, minimum here, right? But the sound, when it's light, it's bright and dark. When it's sound, it's loud and soft. Yeah. Yeah, yeah. They'll make each other cancel out, right? Because if the outer phase now, 180 degrees mean what? Outer phase, right? So if the outer phase, at those points, they will get destructive interference. Okay? So at O1x, they will get a minimum. All right? If you won't get zero, you'll get a minimum. Huh? Oh, what does phase mean? So right now they're in phase. So they're meeting up like this. Crest meeting crest, trough meeting trough. So you'll end up with something larger, constructive interference. But if they change the phase, a crest will then meet a trough. So when they meet up, you will get that minimum. All right, nice. Next one. Oh, it'll take 5 minutes.
We have a promise. I'll bring them up.
All right, so here, I give you an order. Ah, huh? I am starting back at 7:55 to do a next one, and then I got refraction to do. Right, take a small break. You'll do lost hours. Yeah. Huh? Yeah. Right, take a small break and then we do our next one. Siri, just pull it left. Pull it left, man, up, please. Piano. That's what it's called. Get the results section. Yeah. I want to sit down to 6:55. 7:55, I want to start.
Excuse me. Take my jacket. No, we should. Sir. Sir. Sir, what is this? Only his jacket, no machine. I know. I have one. I have one. If you would like.
Hey, fucking hard boy.
No, I have a.
Ignore C, we have to do A and B, right? Let's start back there. Let's take a look at A and B. What can I take it as? A and B. Let's start there. I'm gonna do one from.
You want to have the answer, right? You want to have the answer, do so. And then pick up the question.
Oh yeah, let's take a look at A and B and do the whole thing. Consequent question, please. You can't shoot. Send question. Huh? This is oh no. Yep, oh no. Huh?
Well, like that usually
Yes, very. Yeah, they come from. All right. In order of the wave, explain what coherent. What does coherent mean again? Constant phase. Constant phase difference, same frequency and same wavelength. Nice. What they asked in point B part 2. What are you asking for in B part 1? Sorry, B part 1. A diagram. Very good. You can look at that diagram there. What are you asking for in B part 1? Right, with the aid of a diagram. Because some people will just draw a diagram and hope they get the full mark. Instead of with the aid of a diagram, find why. So you have to do the long thing on the board. Alright? The whole proof. Yeah, the whole proof.
So 5 marks?
5 marks. Alright. So B part 1 is on the board. Let's make a note of it, right? B part 1. B part 1 is the proof. Try B part 2, please.
0.56.
What? Work it out. Work out B part 2. I'll bring somebody on the board. Shivish. You'll do B part 2 from on board.
Wait till that 0.56 wrong.
This one is like a 12 or 14 or something. I'll do a recent FA now, right? After this one. Oh yeah, we'll call B part 2. We'll call B part 2. Create the sound of an area and Azaria to work it out. Hurry up. B part 2, hurry up now, it will take long. Oh, the action was to reach. Hurry up. What the formula is for B part 2, Shirish? Huh? Yes, you do one formula for the class. So we use that same formula. Okay, now, man.
Yeah.
As an example by yourself here, here. See ya? Think so much? Right. What is the 0.2 Azaria? Do you say it, Azaria? What is 0.2? What letter? What is 0.5? T, nice. What is 1.4? Y. And find for the algorithm. Let's check on Instagram. If I forget something. Outside of that, right? So it's all for that. Finish already? Finish already? Down fast. Time for lambda. That's how we can do it. Yeah. Well, yeah, use the correct SI units, please. Why is it not yet? Did I share that? No. Right, so it will be YA all over D. Please remember to work in the right units, right? Actually, the millimeters will cancel off. So everything is on a good cancel off because they're on top. Right, so it's 0.0002 multiplied by 0.0014 divided by 0.5. How much you got for lambda? Should be, How much? 5.6 by 10 to the minus 4. Yeah, it should be a little bigger than that, minus 7. Anybody got minus 7?
Minus 4. So the minus 7 is with the answer in nanometers.
I know, but if they ask in nanometers, nano is minus 9. So the answer should be around minus 7 meters. Anybody get minus 7? Check it back, please.
So when they minus 2, so you get minus 7.
Huh? Right, you get minus 7. So it's 5.6 by 10 to the minus 7 meters. So the answer is 560 nanometers. How?
It was 5.6 by 10 to the power 7 meters. To the power minus 7 meters.
Yeah. So it's 560 nanometers. Nano is 10 to the minus 9. So you have to move the point. What you say? If you have 5.6 by 10 to the minus 7, in order for you to get nano, nano is minus 9, right? So you're going to have to move this to the right 2 more. So you move it 1, 2, and you'll get 560 by 10 to the minus 9. Check it and see. If you move this 2 more times, it becomes 5.6, right? And you will go back to this value here. So 5.6 by 10 to the minus 7 is the same as 560 nanometers. Right? And these questions supposed to be around there, right? 560 is like yellow or one of those colors down there.
So what is the first 5.6 by 10 to the power minus 7 meters?
Same thing.
Minus 9 meters.
All right. I'm going to do it slow bit. Watch this one. So the answer we got was 5.7 by 10 to the minus 7, right?
Yeah.
Sorry, 5.6.
That's in meters.
Right, that's in meters. So I'm going to move it for you 7 times. 1, 2, 3, 4, 5, 6, 7. Right? So the answer is 0.0. 0, 0, 1, 2, 3, 4, 5, 6. 5, 6 meters. That makes sense?
Yeah.
Right. I want to put that in nanometers now, right?
Yes.
So I want to put that in nano. So I want to move it 9 times to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 560 nanometers. So you went the wrong way there. You just picked it up the wrong way. Good. That's how I got to nano. That's okay? Are you okay with that? Soraya, follow and on. So for you to go from minus 7 to minus 9, you have to move the point to the right one. Right?
So you reach up in 7.
You did not reach 1 When I send the message, it was 7.
So you said it was 1 second to 7 meters. Deviation
Actually, Nadia's over here.
I was here.
You're last year before. Okay, now we keep. All right. Let us do one more now. No. And then I want to just talk about refraction and then.
So we need 19 minutes.
19 minutes is all we need. Follow on the food.
What's your that makes sense.
All right, last one. Right, the first part of the question, again, they want the proof, right? This time it's 4 marks. This time it's 4 marks, right? I don't have it. Hey, can't get it back. All right, do this one, please. Sorry, you can't do the question. The answer to client. Come on, let's see if we can do one more after this. Shivish, let me do one question, please. One. Nikash, one question, please. Right. I'm gonna show what it is, right?
I want you to side by side.
So, we have it minus 7, right? So you want to get some understanding. So what do you do to go to minus 7? So what does divide? 2, right?
Yeah.
So I do it a long way again. Right? So you have 5.6 by 10 to the minus 7. You want to get this equivalent to 10 to the minus. Oh yeah, should be sure to put this chuck in, please. I want to do all this. 10 to the minus 7, right? So you want to get the equivalent. So I just do it a long way. So minus 7 means 1, 2, 3, 4, 5, 6, 7. Minus 9 means 9, right? So you come back 7. So
okay.
right, so like if you have 0.003, and that will be 1, 2, 3, so that will be 3 by 10 to the minus 3. If you want to get minus 5, 2, and so on the 5. Right, oh yeah, everybody should be working. Everybody should be working. Sharp. No? Levi, right? Levi. What is it? I'm going to Levi. Sharp or something. Oh, it's 4 friends. All right, they wrong Levi. Give me the message before. Give me a number 723. 72305. Right. Oh yeah, work out the wavelength. 0529. I know you came with one-on-one thing. Sorry, please. I'm just gonna picture it, mother's issue. The last time, right? Right, so you have Young's double slit. What value is this here, Shavish? What's this here? What letter? What letter is that? What's the formula we use in Shavish to find lambda? Huh? Shavish, how much formula did you do to this whole class? Huh? wavelength. They didn't specify. Yes, should be the formula we're using is y is equal to d lambda on A, right? Lambda is equal to y A on D, right? What was y here earlier? Oh, right. Why did you divide by 3? Right, so 4 fringes mean 1, 2, 3, 4. So the separation here is 3.6. So how many y's in between them? You have 1 here, 2 here, 3 here. You see that? So although it's 4 fringes, right? Although it's 4 fringes, you have 3 separations, right? You have 3 spaces here. So therefore, y will be 3.6 by 10 to the minus 2 all over. Well, all over 3, right? And A is how much, Azaria? A is how much? 0.56 by 10 to the minus 3. And D is how much? So we got lambda to be
8.4 by 10 to the power minus 7.
right. For those who are the lost there, what is that in nanometers?
800.
Okay, right. Just one more thing to talk about today is refraction. One more thing to talk about today is refraction, right? So we're going back to things that you kind of know already, right? That's refraction. Random questions. I'm gonna run through refraction as all right. So, all right, let's take a look up here. Let's take a look up here 5 minutes, right? What is refraction, right? We know what refraction is. It's the bending of light as it goes from one medium to the next, right? But we need to understand this notation here. What is n to 1? What is 1 to? What is 1? What does 1 and 2 mean? Like of what? What does 1 to 1 mean? The refractive index of what? Of medium 2 with respect to medium 1. So what's this here? I don't know. Keep looking. You have your normal, right? Take a look on the screen. Take a look on the screen. If you have a ray coming in here, that ray is in medium 1, right? And it's going to medium 2. So what is doing the refracting there? Medium 2. Medium 2 doing the refracting with respect to medium 1. That's okay? Because it's going into medium 2. So medium 2, right, is what doing the refracting. So you would recognize the notation is, the notation here will be 2 first, 2 second, then 1. So the refractive index of 2 with respect to 1. That's the way we write it, right? Right, Saraya? And the formula will be sine theta 1 over sine theta 2. Does it give it up? Right? This here is the other way around. The refractive index of 1 with respect to 2. Right, Shivish? Yeah? Yeah? Right. Shivish say yes, so you want to stay back tonight. That's why I say yes, you want to stay back tonight. Right? All right, nice. Good. Just quickly, just make a note of this, right? Right. Please remember that refractive index is also a speed in medium 1 over speed in medium 2, wavelength in medium 1 over wavelength in medium 2. Right? What remains the same during diffraction? What remains the same during diffraction? What? You sure? So the wavelength don't change? Speed changes, right?
Yeah.
Speed changes. Does the wavelength change?
Yeah.
Yes.
Yeah.
What stays the same? The frequency. Frequency stays the same as they go from one medium to the next. Alright? Look at it there. Angle changing, speed changing, wavelength changing. Alright? Frequency not change, alright, Aria? Right? And there's also this relationship. You can also use this relationship here to represent refractive index. Please remember, what does N1 mean? What does N1 mean? Refractive index of the first medium, right? With respect to air. Right? So you always assume air. Okay? So this is the refractive index of medium 1, this is the refractive index of medium 2. So if you don't have this, if you don't have the refractive index of 2 with respect to 1, then you use this nice relationship here. Okay? Right? So let's add that to the list, right? Right. Anybody remember this? Right? As the ray enters, it undergoes refraction. As it comes back out, what you have? Same angle, because the emergent ray and the incident ray are always parallel. Ray, not the angle. The angle is equal. Alright? You have a deviation here. What about critical angle? Anybody remember the concept of critical angle? Right. So for example, if you have a air-water medium, right? And you have a ray of light coming in here. If that ray of light travels along the air-water boundary, this angle here is called your critical angle. Okay? How you find critical angle again? Sine inverse 1 over the refractive index. Okay? And what will happen if if the angle of incidence is more than the critical angle and it's in the more dense medium? What has happened? Total internal reflection. Okay? So just some small things to remember, right? So you have to remember those three things, right? In order for total internal reflection to occur, what must happen again, Shavish? The angle of incidence must be more than the critical angle, and the ray must be in the what? Denser medium, right? All right, we'll do a question on this next day, right? All right, so we'll take a look at refraction next day, a quick question, and then we'll do some. I had a quick note. Right, and then we'll take a look at diffraction.